Hello all. So today we are going to see this that numerical solution of using MATLAB. You can use Python also, but algorithm remains same. So that's not a big deal. Okay. So I hope you remember the problem statement and the governing equation. So it was a PDE basically of either velocity or stress, whatever is given in that problem. I am assuming it's a velocity driven flow where the bottom plate is at some velocity v naught, let's say 0.01 meters per second, and the top plate or the top layer is very far, and that will always remain stationary. So I'm assuming there is another plate at the top at height h where the velocity is 0. So we have our governing equation, right? So let's do this, how we solve it numerically. So before that, let me show you that what this MATLAB, sorry, MATLAB is not here, it's here. So MATLAB is nothing but it's matrix laboratory. So everything, uh, is in terms of matrix. So let me show you a few operations. So once you open the software, that's how. So you'll see that the first window which will pop up. So just wait. Right. So you will see this command window here it is written, and then this you have to wait because two arrow sign will appear. Then now it is ready. You can see these two arrows. So this command prompt is or command window is to run something instantly here, or results will come here when you will run your code. So when you write the code, if you go here, you see there is a script button. So this is script, new script, and whatever you write, it saves the file in the form of you know uh, that .m file. So you can run your program here and you can save it. That's what we'll do. But before that, I can show you a few things here itself in the command window. So let's say if I write x equals to, right, do this sign 1, 1, 2, 3, 4, 5. So I have created a matrix. Okay. It will now, let's say if you access x of 1, it will give you 1. Let's say if you say x of 4, it will give you 4. Let's say if you say x of 1, or let's say if you say x of 2 into x of 5, it will give you 10. Okay. So everything in MATLAB understand in terms of matrix. If you say CLC, it will clear your command window. Okay. What else? You can solve the equation also. That's very easy. If you have an equation, let's say x equals to b, system of equations, then you all know x is a inverse b. So for example, let's say we have x plus y equals to 2, or let's say x plus y equal to 3 and x minus y equal to 1. Answer is 2, 1. Let's see how you can solve it. So when you say x plus y equals to 3 and x minus y equal to 1, you will create a matrix, your unknown matrix, and your B matrix. So unknown matrix is a column matrix having variable x and y. Okay, that will say capital X, let's say, and then your A is 2 into 2 matrix. So let's make first 2 into 2 matrix. How we write it? Let's say I write A equals. So if you see the coefficient, x plus y equals to 3. So the coefficient is what? 1, 1. Okay. Then you say enter, and then the coefficient 1, and then we have -1, and then close it. Let's see this. So this is our A matrix. Unknown matrix we want to know. Capital X. Capital X is nothing but a column matrix. Small x, small y. And B is what? So x plus y equals to 3 and x minus y equals to 1. So it's a column matrix. So let's say B. You can always say, let's say B equals to uh, 3. You can say write this way also. Let's say if you write B equals to 3 and 1. It's a row matrix. But this is not your B. So what will be? So we can always say, let's say new matrix C equals to B prime, that is B transpose. So C is 3, 1. So Ax, our equation is in the form of matrix Ax equals to C. So X will be A inverse C. So what we are going to say, X is a new matrix, the unknown matrix, X is equal to A inverse, that is INV of A into C, not B, because we need, this column matrix. I think answer should come. Let's see. You see, it gives you answer directly 2, 1. Because when you will use the Crank-Nicholson or simple implicit method, okay, uh, basically you will for a given time, okay, for let's say for any time step, let's say time step kth time step, or let's say fifth time step. So for knowing the variable of fifth time step, let's a fourth time step will be known. And for fifth time step, you let's say you have 10 grid points, starting from bottom plate to top plate. Time step is known, and you want to know what fifth step, except grid 1 and grid 10, because these are two boundaries. So for that, this Crank-Nicholson and this simple implicit, when you will write those equations, it will take a form of such kind of equation, where all the t's at fifth fifth time interval or fifth iteration of time is an unknown matrix. This whatever we have said A here, that will be known to you, because that is in terms of 1 and in lambda and another things like diffusivity and whatever. So that will be known, A will be known to you. Right hand side, that matrix C will be known to you. Okay. And then, so what I mean to say is as follows. If you'll see this, where it is here, yeah. See, if you use the simple implicit or Crank-Nicholson, right, you will see this formula or this formula, right? And first of all, you can write it for, let's say, I equal to first node, first grid point, and I equal to last grid point. Because for these two grids, first grid and last grid, are the boundaries. And for any time t, these values are known. One is u naught, some velocity, another one is 0. Okay. So since it's known for any time, okay, so and you know the initial condition also. So first time step, so let's say whatever t the first time grid values are known. So you want to know the value at another time step. So let's say if you see this Crank-Nicholson, okay, and if you take, let's say, k equals to 1. So whatever is the value of I, sorry, so you take k equals to 1. Okay, so at k equal to 1, everything is known, the first time step. Why? Because it's an initial condition. So in the whole domain, that velocity value is 0. Okay, except at boundaries. So boundary you have to take care when I is either the first grid or the last grid. Accordingly, you have to take care. Okay, so basically what I'm saying, that due to the initial condition, at first time interval everything is known. You want to know in the second that value for the second time interval. That's why if k is 1 here, you see on the right hand side k is 2. And then the I, what you see is that for the nodes on that y-axis, right? The space coordinate. So you will get some equation. And that equation will, when you will arrange in terms of ax plus b, A will be a tridiagonal matrix. X will be your this unknown temperature at k plus 1th step, or let's say if you know first step, the second step, you want to know what are the value of the temperature, and right hand side is known to you because it's the at the previous time step. So you'll come to know when you will solve this equation the way I solved it, you will come to know the value of v at second time step. Then you will use those second time step values to know third time step and so on. Okay. So I just given a overview to you. Now let's solve. I will just show you this explicit method and rest you can do because the rest is matrix operation. Here it's a bit simpler. Okay. So what we are going to do. So as I told you, we'll write a M file. Okay. My screen is shared, I guess. So this is where is our M file? Let's see. No, not here. Here. So this is our M file. Yeah. Right. Dot M file. So first of all, you write in the program CLC clear all. Why? Because this command, whenever you will run your program, it will always clear the command window. So the previous things will not be there. Your command window will be clean, right? Okay. You can define the various values. Let's say viscosity of water is 1 E minus 3. I'm putting everything inside units. MATLAB doesn't know units, so you have to take care that you put values correctly. Density of water is 1000 kg per meter cube. Okay. And then what we have is, remember, if you want to treat a separate value, you have to use this semicolon. Okay. Only comma will not work. Only comma leads to a matrix creation. Okay. Now we can calculate this momentum diffusivity, MD, which we have said nu is nothing but it's mu by, no, first this is kinematic viscosity. And that is, yeah, that is the momentum. So mu by density, right? So this is done. Now let's say we'll choose our height. So height is, let's say, 0.01 millimeter. Okay. And we want to know the velocity matrix, right? So let's just create an L matrix. And now let's say that I'm dividing my this whole domain in 10 grid points. You can go for more. You have to just make sure that lambda which will create should be less than half. If it is greater than half, the solution will not converge. So n is 10 and delta y or delta x, whatever you want to say, I am defining it as height divided by n. Okay. This will be my delta. Right. Okay, time step, let's say the time step I'm using m and I use, let's say, 10,000 time step. This much is enough, right? And then I say delta t is equal to 0.3. So you can calculate the total time. It's simply delta t into the times 10,000. Okay. Right. So this is done. Let's define our lambda also. Since we don't need right now command prompt, we can minimize it here. And whenever we're needing it, we'll bring it up. It's here is the command window. Okay. So let's minimize this currently. Minimize this also. We don't want this. Minimize this also. Yeah, so all these things are a command window, current folder, workspace, right? So this is done. Lambda, right? So lambda is nothing but LT. Let's see the lecture, class lecture. This divided into K, which is nothing but momentum diffusivity, new MD, any kind of diffusivity, that divided by delta y square. So del y is our lambda, and you have to make sure whatever time step or this delta y you are choosing, lambda should be less than half. Right. This is done. So then let's create our time matrix. So if whenever you're writing a program, you always use this percentage button. This is like, this is not a command. This is just for understanding the problem. So I'll say time matrix. And you see first time, so I'm creating a time matrix. So time of 1 means the first element of my time matrix is equals to 0. And then I will run a loop for, let's say, j equals to 1, 2, sorry, 1 is 2 is to n. I will set time of j, right? Time of j is equals to simply j into del t. Now, whenever you write the program up to whatever point you have written, if it is solvable, you should solve it. So let's say if I solve it, I'll open the command window just to check whether my time matrix has been created or not. So I will say, where is the run? Yeah, here is the run green button. Okay, so run. Okay, so first I have to save. So let's say I saved on desktop, and I'll say unsteady state. Save. Oh, it is saying this name is not valid, so there should not be any space. So I will just save. So you have saved a M file, okay, and then change folder. And if now we see command window, you see, so it is typing del t is 0.3, okay, because you have given a comma, right? So it is, so it's better if you don't want to print it, you say like this. And now again run it. So it is done. So if you don't see any message here and only these two arrows and one cursor, it means everything is fine. Calculations are fine. Now let's see, we want to see our time matrix. Okay. So you have created a matrix and you have saved the, uh, what we should call this, various elements, first element, second, third. So in that case, if you type time, if you type only time matrix, it will give you, uh, like this. If you want column, what will happen? So again, I'll clear my command window. I'll say time and I'll put up transpose. This way it will create this. Okay, so these are the various values of this time matrix which you have created. Okay, let's see. Okay, now we'll create grid in space matrix. So space matrix, let's say our first point will be 0, y is 0, 1, 0, okay. And then again look for loop I equals to, let's say 1 is to n, right? And y of, sorry, not 1, because 1 we have already defined, 2 to n, y of I will be simply I into del y. Okay. There are various ways to create this matrix. This is just one of the end. Just check whether we have correct. So I should final value, there are n equal to 10 and value should be go to 0.01 from 0. So I'll run this program. So let's run this till this point. I'll go to command window. So everything is fine. I'll say y prime. And you can see from 0 to 0.1, there are 10 points. Okay. With this increment, which is h by n. That is your del y. You can calculate that same gap is here. So grid point is created. I mean, both grids have been created, time grid and space grid. Right. Now what we are going to do? Now we'll define a boundary condition. If you write this like boundary condition, this will be treated as a command. So better you either use percent, or if you'll do here the right click and say comment. So this is just for our help. When you will read the program, you can, okay, this is boundary condition, right? So you see the boundary condition is what? The boundary condition is that Now remember, boundary condition in terms of velocity, which is which has two-dimensional matrix. So V of you have to write I, you have to write Ij. Okay. So what we will do, we will set this way, that for j equals to 1 is to m. Remember, j is the index for time. Remember here. Huh? I mean, this is a local variable j, but just reminding you that m is for time. So j equal to 1 to m. And you say v, boundary condition means 1, and the first grid and the final grid is known. So v1, and then you say comma m. So this is the velocity at the bottom plate. That is the first grid at any time t. That's why j will go from 1 to m, whatever time we are considering. And let's say this velocity is 0.01 meter per second, some value. Okay. Or if you want, you can do this way also. You can define your u0 here. U0 is 0.01. In that case, you write here u0. So this value will be taken from there. Okay. This is done. End. Okay. Now, just to be sure, you can again save and then run and check that whether boundary condition is correct or not. So what we are going to do is, sorry, not start this command window. You want to print the first row of v, like the time grid. So say 1, then comma, and for all time, the second grid is for time. So all you need to do is put this colon sign bracket. So it will give you the value of that first, that bottom, that uh, first point, and then for all time. Okay, because there are two indices in this matrix, I and j. I is for space, j is for time. So you're saying I equal to 1 means bottom plate for all time. You see what we'll get? Let's say prime. Okay, we'll get this. So what you see? You see here that this is 0.1, and then for rest of the places, so it is, oh, it has wait, let me see what it has given us. So j equal to 1 for all time, it is u naught, fine, and for rest it is 0. Where is the problem? Let me check. This is fine. U naught is 0.01, so all values should be u naught. Why it is taking 0? Let me see. Sorry. Oh, sorry. You see, it should not be M, it should be J, right? So V1J, this is J, which is going from 1 to M. I used M. M means it was only giving me the final time grid value. Okay, now it should work. So that's it, right? So 1J, so 1 is fixed, the bottom plate, and time is varying. And for all time, it is U naught. So now it should work. Run this. Let's see the command window. Many times we can keep command window like this also. Huh? We don't need to minimize it. So nothing, no message. So it means program is fine. Now let's type this v1. Now it is everywhere. It's 0.1, 0.1, 0.1. Okay, throughout the grid. Sorry, not throughout the at bottom point for all time. That's why you see so many values, because it's for whatever time it is at all time grids. At point bottom point will remain at uh, what 0.01, that you note. Another boundary condition. So for that, for again control C, I can do control V, but this time this point is what? This point will be our N. Okay, the last point. Are you getting my point? That first grid and last grid, Y grid is a boundary. So 1 and now N. N is fixed 10. And there we know it is 0 always. Okay, so 0. That's it. So boundary condition is done. Let's check if you want. Let's check Vn, that last space grid. What is the value? So you can always say like this, and I'll change it rather than 1 to me check, it's 0 everywhere. Okay, just give me a moment. I have to take a call. Yeah, sorry for the interruption. There was an important call. Right. So where we were, you can see that I've just when I was talking over phone, I just typed this, so it is 0 everywhere, right? So this is done. Okay, now what we do is so we have done this now initial condition. Sorry, boundary condition is the initial condition. So again, just for clarity, when you read this program later on, let's put this percentage. This is, let's say, define initial condition. Okay. Let's make space here. Marking here. So for initial condition, now remember that the grid value will change, space grid, and time grid will remain same. That is first time one, which is 0. What we are going to say, v, okay, and then first we have to run a for loop. Let's run the for loop. Now you see here you have to be careful, and this we discussed in the class also. This doubt was raised. Remember, when you are defining initial condition, you cannot include boundary. Boundary always remains boundary. It should not be included in, it never should be included, cannot be included, or must not be included in the uh, initial condition. So that's why j will start from 2. Okay, not j, sorry, we are dealing with I, right? So okay, space grid will start from 2. Not only that, you can guess it can only go, and not m, our space is n, right? So I will go from, as you can guess, 2 to not n, because n is also a space grid. So 2 to n minus 1, right? And then what we are fixing is the this last this second interval time we are fixing, that is first time step. So we will say it is 1, right? And what will vary now is I. So you see carefully what I have done. I cannot include boundaries in the initial condition. So I will start from 2 and it will go to n minus 1. Okay, the second last grid, and then uh, space grid will this time run over this loop, and time is fixed, the initial condition, and that is also everywhere 0. Okay, so this is also done. You can print it and you can check it later on. Well, so everything is done. Now the only remaining thing is writing this formula here. Okay, or it's here also, I guess. Yeah. This formula, which is simply sorry, this one I'm doing explicit method, right? So ti of k plus 1 should be equal to ti of k plus lambda times this. Okay, let's do it. So again, you have to run the for this time you have to run 2 loops. Okay, because both time grid and space grid needs to be updated from the previous information. So for I equals to, as you can guess, I cannot start from 1, it has to start from 2, and it cannot go to n because these two are boundaries, values are known. So I'll go from 2 is to n minus 1. Okay. Then within space give time grid for, let's say for time I use k equals to, and time will go from, so only initial condition is known, t equals to 1, means time of 1, that is 0th second. So it will go from 2 is to that final n, whatever time it is. So, right. And then what we are going to update is velocity. So it will be v of I and k. So velocity at I and k state, that will be equal to velocity I at k minus 1th state, okay, plus lambda time. This will be v of, okay, so let's see the formula, what it is. Lambda time, everything is in one single bracket, right? So lambda times, this is v of I plus 1, k minus 1, close, and then minus 2 times v of I, k minus 1, and then plus v of I minus 1. Okay, you can take the formula. Okay, that's it. Bracket closed. And if you don't put here the semicolon, when program will run, it will keep on printing it, and unnecessary or time will be consumed. So put this semicolon, so that if you don't put semicolon at any formula, what will happen? It will keep on printing the value and loop will run. Oh, here it should be a star, which is missing. You see, if you don't put star, it will. So whenever that's red, now the red has gone. Okay, why this is still here? Some. Achha. Now we will say end, and one for loop is closed, another for loop is closed. Still this thing is coming, so there is some problem here which you have to check. V of I k minus 1 plus lambda times V of I k minus 1, this is closed, minus 2. This is one extra thing here. V of I k minus 1, right? Plus v, now it is fine. Whenever you see, let's say if I put extra bracket, just I'm showing you, this red thing will come. It means there is some problem with, so of course it is not there, right? So this is done, okay, and that's all I think, because it will start running from t equal to 0. At t equal to 0, all the values are known, so it should give us the answer. So it's better we plot the answer. What we'll do, we will say plot, and let's say I want x-axis, on x-axis the velocity, and on y-axis the y grid. So I will say plot x-axis is, let's say I want the information at for all y at first times 1. Okay, it will give me at okay, and then let's say I say v, this is what, and this is y velocity, and okay, so this is for first time step, right? V1, and then y, and let's say in red color. Let's close it. You want multiple plot, let's say hold on and say just copy paste this for C for V, and let's say you want to know at 10. Okay, 10th time step. Again, hold on, control V. This time you say you want at 100 step. Okay, hold on, and let's copy this 2 times, and it's 1000. and let's see. So this we can say 1000. And the last one is 10,000. Yeah, and then this is, if everything is fine, we should get plot. Let's run this, and here is your plot. Okay, oh, everything is red. So just to distinguish, rather than one, we can ask it to, second one, and red, blue, green, and last I say, let's say star. So that's it. That's how you get this velocity profile. Okay, I'm just wondering, oh, probably this is a older, version. So all the curves are coming in red. What if I remove this star and I just leave it like this? Okay, I pick the curve. This is just, you can learn how to do this multicoloring plot and all this in MATLAB. That's not an issue. Or in Python, whatever other way. Ah, now we are getting different color curve, but this green is not coming. So maybe there is some different command. But yeah, so that's how you will get the velocity profile. You can see that our velocity is going, so this y equal to 0 is always at 0.01, and this velocity plot is shifting towards higher time in this direction. Okay, and this grid is going from 0 to 0.1. So do this, and we will be needing such code in future also. When I'll get some time, I'll tell you there are libraries which you can use directly to solve these PDs in MATLAB itself. Okay, that also you can do. So in fact, from future onwards, I will not tell you the name of the method. Whatever method you want to use, solve it numerically. Okay, so we have written this code, Crank-Nicolson. Try the Crank-Nicolson one. But there are libraries also, PD libraries. They take care of whatever method MATLAB is going to use, that library, and it will give you the final answer. So you can have a Google search on that. It's easily available. Someday I'll share that how we can borrow the PD library, okay, from MATLAB. Okay, thank you. Thanks.